Our next presentation is going to be utilizing an application-heavy perspective on phosphorus removal from the basics of field observations. And here to tell us more about that is none other than Adam Jennings from Hach. Adam, take us away.
Hi, thanks, Travis. Glad to be here today. Appreciate the time. We'll get into it. So I'm going to talk about maximizing phosphorus removal. We'll go over some lessons and things that I've learned from being out in the field. I get the pleasure of seeing lots of treatment plants and how folks are doing things. So we'll talk about some of the basics of biological phosphorus removal. We'll briefly talk about the ways that we can remove phosphorus chemically and biologically. We'll get into a little bit of lab monitoring, some online monitoring. So, what are we trying to do? What's the goal here with phosphorus removal? It's a unique process, whether we're doing it chemically or we're doing it biologically. Either way, the goal is to remove phosphorus as a particulate. So you can see here on the left side of the screen, we have the general forms of phosphorus that are coming into our treatment plants. Largely orthophosphorus with some particulate. And then after treatment, you can see that the goal is whether you're using chemicals to create more particulate phosphorus or you're doing it biologically by using microorganisms. Either way, we want to settle these particles out and we remove phosphorus in a physical form. Unlike some of our other nutrients where we might be removing chemically or just strictly biologically. So what are the different ways that we remove phosphorus, the combinations? So what we do is we have full chemical treatment options where we are just using chemicals in a system in various locations throughout a treatment process to remove phosphorus physically using chemicals. We can also do it strictly biologically. There are certain types of organisms that remove phosphorus, and we can capitalize on that. And there are some benefits and detractors from both of these different ways. And then some facilities we will do both. We'll remove phosphorus biologically, and we try to do it primarily biologically. And then maybe we'll have a trim system using various metal salts to trim the system. And this can be exceptionally helpful when our facilities have very low phosphorus limits. That can be helpful. So some of the key challenges, if we're doing full chemical treatment, it can be a pretty high operating cost. There are lots of things to think about when we're adding chemicals and what that does to our entire system, including potential alkalinity reduction and pH issues. Most facilities have pH on their permits, and so if we're lowering the pH due to the addition of these chemicals, we might have to add something to increase pH. Biological treatment can be challenging. It's a difficult biological process to control. It's very environmentally dependent, and then the combination. We get a little bit of the benefit of both. Maybe is my opinion on that. So we can do majority of it biologically, and then trim with chemicals. So in a biological system, what does that look like as far as how a treatment process works? Well, if you're doing biological phosphorus removal, which is what we'll primarily talk about today, you have an anaerobic zone. You're going to need an anaerobic zone to do that process. And it's important to know what that means exactly as it relates to dissolved oxygen and combined forms of oxygen, nitrate and nitrite. So anaerobic zones, maybe it goes without saying, but no dissolved oxygen should be present if we're going to call it an anaerobic zone, and no combined forms of nitrogen or nitrates or nitrite or nitrate. And then you have anoxic zones will also not have dissolved oxygen, but you will have nitrite and nitrate by practical definition. So these combined forms of nitrogen are present. And then oxic or aerobic zones, you have dissolved oxygen, of course, present. And is there nitrate or nitrite? It doesn't really matter from a biological perspective. These organisms will go after the easiest oxygen source available. So if oxygen is present, free oxygen, they will use that over combined forms. And so it's important to know this because when you are trying to achieve biological phosphorus removal, the anaerobic zone is key. And so this has a couple of different things on it, this chart. So we have ammonia coming into an anaerobic zone, phosphorus, nitrate, and some systems have internal recycles for removing nitrate out of their system to denitrify in an anoxic zone. And the key here is just to focus in a little bit on this red line. So phosphorus levels could come into a treatment plant between 2 and 5 milligrams per liter. And then you can see what's happening here in an anaerobic zone. We're increasing phosphorus levels pretty significantly, which seems counterintuitive, but that is actually part of the process, and we want to do that. And I'll talk more about that here in a little bit. And then you can see that the phosphorus levels will decline even through an anoxic zone, and then of course through an aerobic zone as these organisms uptake phosphorus. There are a lot of things to consider when we're doing biological phosphorus removal. Of course, classic things like the loading that's coming into our treatment plants, flow changes, side streams are notoriously difficult to understand, and then the challenges that come from say an anaerobic dewatering system where you have very high levels of phosphorus or nitrogen coming back to the treatment process. Those loads can be very significant in how successful we are removing phosphorus. Diurnal conditions, seasonal conditions, temperature, SRT control. Sometimes when we think about phosphorus removal or even nutrient removal in general, we don't think that how we manage our solids are as impactful as they are. And maybe we continue wasting in certain manners throughout our system, and they might not be adequate, especially at low levels for phosphorus removal. There's competing biology. If we're trying to remove forms of nitrogen and phosphorus, and we're doing that both biologically, there are some real considerations and the challenges that run into those things. Secondary system phosphorus release. If you have secondary clarifiers, solids that are held in those clarifiers can release phosphorus and add that to your effluent. And it may be something that's missed depending on how sampling is done for process control. Air entrainment in the anaerobic zone, solids and effluent. There are phosphorus is in all the solids that are coming out of our treatment plants, and that can affect our overall phosphorus removal. And sometimes, depending on how the system is configured, we can run into issues like struvite when we're removing phosphorus biologically. So lots of things to consider, lots of challenges that could be discussed in detail. But just as a note, these are some things we can look at. So the basics of biological phosphorus removal. I like to break it down into three main categories. Number one, we need to make sure we protect the anaerobic zone. If we don't have a good anaerobic zone, that will reduce our amount of phosphorus release, and our increase coming out of an anaerobic zone won't be as high as it should be, and maybe we might have issues treating for phosphorus. Having an adequate supply of readily degradable carbon in the form of volatile fatty acids is key. So volatile fatty acids will be used for denitrification. And once denitrification is done in an anaerobic zone, if there are nitrates present, then we can start increasing the phosphorus levels. And then removing phosphorus, these organisms need aerobic and anoxic detention time to give adequate removal rates. And so of these three things, the thing I see the most is challenges with nitrate coming back into an anaerobic zone, which is a pretty common configuration. And those nitrates use up volatile fatty acids, these precious carbons that the organisms that do phosphorus removal use to increase phosphate levels in an anaerobic zone at a rate of about 2.8 milligrams per liter of volatile fatty acids used up per nitrate denitrified. So if you have lots of volatile fatty acids, then it might be working out just fine for you. But if you don't, which is very common, then every milligram per liter of nitrate in an anaerobic zone is a big deal. So when we're protecting the anaerobic zone, there are a few things we can look at. So submerged mixing, if you have really high energy, mixing energy, you can actually create vortexes and other agitation that can entrain oxygen into that zone, reducing its efficiency. If you have primary effluent that goes over a weir, then that could also increase oxygen into an anaerobic zone. And of course, if you have nitrates in the RAS or low carbon, all of those things can really hinder how well we remove phosphorus biologically. Internal mix liquor recycle also can bring back air if you have that for denitrification into an anoxic zone. So things to consider. So as a whole, this is what it looks like. You have a certain level of volatile fatty acids coming into the treatment system, around 12 to 50 milligrams per liter. And those are being used up as a sort of a life battery for these specific type of organisms. Polyphosphate accumulating organisms is what they're called. And we're trying to increase the phosphate level, of course, as we've talked about, to a much higher level. And that's the key to beginning the biological phosphorus removal process. So this is just an animation kind of showing what that would look like. You know, we have certain 2 to 7 milligram per liter phosphorus coming in, and we increase that up to a much higher level. And then as the organisms then get some combined oxygen, they can start removing or uptaking phosphorus again into their cellular mass. And then as we move through the aerobic zone, the phosphorus gets removed even more. These organisms continue to uptake phosphorus. And then in the end, we end up with this net positive phosphorus reduction that happens. And this is what we call luxury uptake. And so in a quick basic example of what biological phosphorus removal looks like, the key here is making sure that we have this luxury uptake, and the anaerobic zone and carbon is all a big part of that. So from a process perspective, what can we do right now to help ourselves understand what our current state is and maybe what we need to do? And so primary treatment, it's some of the things we can test for. We can do lab testing, grab samples where we're filtering samples on site at the treatment process, and we're getting a snapshot of what our volatile fatty acids look like coming into our anaerobic zone, understanding the phosphorus levels. And then once we've got that data, we can look into our RAS nitrate, make sure that that is an appropriate amount, appropriate rate for our volatile fatty acids that we have coming in. We can check our phosphorus levels coming out of the anaerobic zone, which are hopefully high, checking nitrates coming out of an anoxic zone, and then also seeing what kind of uptake we have with phosphorus, orthophosphorus testing. We can look at the end of the aeration basin for phosphorus and potentially some other things. But it's good to know this level of phosphorus, because if we check after a secondary clarifier and we have a higher level of phosphorus, there could be some level of increase in phosphorus because of high solids in the secondary clarifier. So just a quick look at what we can do if we need to go beyond lab sampling and grab sampling. There's a lot of things on here. These are all sorts of things that can be monitored in real time. And but for the purpose of this conversation, I just wanted to focus on a few that help with phosphorus removal. Biological phosphorus removal, we can do ORP in an anaerobic zone to understand how anaerobic it is. We can look at phosphorus coming out of an aeration system before a clarifier. We can make sure we understand in real time nitrate concentrations in RAS rates, and then effluent phosphorus. And then there are a number of different things that we can test for, and here's some examples in the lab. So that rounds out the quick discussion on phosphorus, biological phosphorus removal, and appreciate the time. And please feel free to reach out if you have any more questions. Thank you.
Thanks, Adam. Much appreciated. A lot of good information in there. And for all of you who would like more information on what Adam just covered, please feel free to reach out to them directly. at the contact information that you see on your screen right now. And of course, if you'd like more information on Hach, not only can you find it on their own website, but also here at Water Online.